So hello everyone, I welcome you in my class. So longitudinal autopilot design is completed. Now we'll move to the lateral autopilot. So we'll start with the simple actuator modeling like we have done in the case of longitudinal case, like what we have modeled, how we have modeled like actuator dynamics, delay, and then we know that using part approximation you can actually account for a delay. Okay, and then the lateral autopilot design. In lateral autopilot design we will use the aileron to control the roll rate. That is how we will obtain the in this lecture aileron to load rate transfer function, and then we will move to the roll rate control loop, and then finally roll angle control loop. So the actuator modeling and delay is same what we have done in a longitudinal case. So I request to go back to that lecture and please see how we have done. Okay, so now this is a typical roll attitude loop. So the best way is to understand, like, replace theta by roll angle phi, replace q by roll rate p, everything remains the same only. Design procedure is same. So first we have to obtain the aileron to roll rate transfer function. So we know that theta equal to q cos theta minus r sin theta. So I can write this q plus q cos theta minus r sin theta minus q. Okay, so this part is called disturbance in dynamics in a longitudinal case. Okay, similarly we can consider the for the roll case phi dot equal to p plus q tan theta q sin theta plus r cos theta. So in this case this part will be the disturbance in phi roll angle. Okay, so in the first step is to obtain the transfer function. So in longitudinal case you have to make equation in terms of theta dot equal to q, rest of the term you treat as a disturbance. Similarly phi dot equal to p, rest of the term you can treat as a disturbance. Why? In controlled design, let's say theta is small, so theta dot will be equal to q, fair approximation, right? And let's say if you have a pure roll motion, you can put q equal to 0, you will get phi dot equal to p. Okay, so in control design you approximate this one, but in reality there will be all the term involved here. Okay, there will be the all the term, so you can consider this as a disturbance, and you have to make a controller robust enough in order to and powerful enough in order to handle this kind of disturbance. Okay, so now, so as of now let's say I am putting disturbance as 0, so directly we can write phi dot equal to p, simple, right, where p is a roll rate. Okay, now if you differentiate, you will get phi dot equal to p dot. Okay, and what p dot you can write? P dot you can write, see what is p dot? P dot into ixx will be what? Rolling moment, right? L. We have seen in the aircraft degree of freedom case, right? Before this, what you can do, you can take a p dot equal to what you can write, then p dot will be L divided by ixx. Okay, since we are dealing with the rolling motion, so we will consider the ixx part, right? Moment of inertia about the roll axis. Okay, what is the rolling moment? Half rho v square s b into cl, right, by ixx, right? Cl you can write this part you can write k into CL directly you write for a simplicity. Okay, so P dot equal to k CL, and CL I can write CL naught CL beta into beta plus CL P PB divided by 2U CL R RB divided by 2U plus CL delta A into delta A plus CL delta R into delta R. This you can write. So this in aircraft design course I have talked about. This is nothing but the aerodynamic model representation in roll case, where CL represents the rolling moment coefficient. This is CL beta, this is the stability derivative, CLP is a damping derivative, okay, and CL delta is the aileron control power. When you there is a coupling involved, so when you deflect there will be roll, so that is why CL delta is written. And CLR, that means when you uh, 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 yeah, there will be roll, okay. So this is a complete aerodynamic model is there. So for a ideal case, what you can do, this if you perfectly design the, there is no manufacturing default, then this CL naught will be the 0, and you can consider while control design, you can consider as of now this part is 0, beta is 0, because that beta you will cancel on using rudder and all. So for a roll control design, you just rely on the pure roll motion, you ignore all the motions. So you can write k, what is the dominant motion, CLP PB by 2U, U or V, that means velocity, okay, and CL delta A into delta A, right? Simple. Agree with me? I have written all the things, but I have approximated and reached to this simple expression. What is the second step? Take the Laplace transform. So when you take the Laplace transform, then you can write P of S equal to K. This is CLP. You can write CLP and P of S B by 2U, and CL delta A of S. Agree? Okay. So you can take S minus K CLP B 2U, ठीक है, okay, into P of S, and this is K CL delta A of S. Okay, so what you can write, P of S by delta of S is K CL delta A divided by S minus K CLP B divided by 2U. Agree? That is how you have obtained the transfer function P by delta. So now you have a plant with you. Okay, go back to this part. Agree, right? So you no need to obtain a transfer function between roll angle to aileron. Automatically, if you consider this loop, it will be taken care, right? If you integrate, you will get 5. Simple, right? So now this part is over. Now you have to put the first position and rate limit. Why position and rate limit? Because it is important, because aileron has a certain limit to deflect, let's say plus minus 15 degree. Beyond that, you cannot deflect 360, right? It's a physical constraint, and you cannot move with so fast, right? There is a actuator, see, there is a hydraulic system involved where when you give the command, it has some power to deflect, right? So you can deflect with the 15 degree per second, not like a 360 degree per second. So you have to put the physical constraint, position and rate limit, and then put the actuator dynamics and sensor dynamics, and include delay and make it a complete plant. So P by delay transfer function with a complete delay and all you have done. Okay. Now, and with position and rate limit and actuator and sensor dynamics. When you integrate P, what you will get? Roll angle, right? Phi. Okay. Now, so when you have deflected the aileron, aircraft will start responding. Okay, let's say in that case the damping was, let's say 0.2, 0.3, but you want to manipulate the damping, you want to increase the damping. What you can do? You can take feedback of P and you can actually have a feedback gain like we have seen in the longitudinal case. This filter is required in order to filter unwanted signals. Now when phi is there, when you integrate phi is there, then you will close the loop using PI controller. Okay, and let's say if you want to command phi equal to 5 degree, then and this is the angle phi equal to 0. Let's say you want to take a turn, so the aircraft is flying phi equal to 0 and you want to take a 5-degree turn, or let's say 30-degree bank. Okay, so when you want to take some kind of turn, then you have to bank the aircraft, right? So let's say 550 equal to 5 equal to 50 degrees commanded for a some second. So you will give 50 degree here. So initial error will be 550 minus 0 will be 50. So this PI controller will generate the roll rate command. Okay, that means if I want to achieve 50-degree roll, that this much rate I have to generate. And who will generate this rate? Aileron. This is aileron is generating the rate. Okay, when you want to attain heading this direction, let's say you have takeoff and the location is, let's say, Delhi, this side, so you want to take a turn, right? So how will you take a turn? First you have to bank the aircraft, right? So that means you have to deflect the aileron this side down, this side up, to make lift L plus delta L and L minus delta L. With this net moment you will roll the aircraft. Okay, so that is how it is happening. You have commanded 50-degree, roll rate is generated, aileron is deflected, and this loop will be keep continue going on till the required bank angle is achieved. Okay, so have you seen this? It is similar to the pitch loop only, right? So as we see in there, when you do the when you have a plant with you, you have to check the natural responses. That means take a nonlinear dynamics, linearize them and find out the modes. So in lateral, what mode we have discussed? Roll mode, Dutch roll mode, spiral mode, and we have also seen that spiral is marginally stable and in most of the cases unstable. And Dutch roll, spiral mode are both are closely associated. When you try to increase the Dutch roll, spiral mode will be I mean to say, when you try to improve the Dutch roll mode, spiral will degrade. Okay, and we will try to improve the spiral mode, then the Dutch roll will create the problem. Okay, and this is a pure roll mode. So three mode is existing: roll mode, Dutch roll mode, spiral mode. Okay, so this mode you have to be very ensure all the modes in a closed loop. When you design the closed loop system, it should be left half the plane in order to make the system stable. So when you do this thing, see P by delay with delay, when you do this with the delay and all everything, you plot the root locus and you can see how my root locus is moving. That means how my roll mode is behaving, how my spiral mode is behaving when I'm changing the gain. You can see so many gain, feedback gain is there, PI gain is there, right? So when you change this gain, how this mode is behave, you have to be very sure, and you should make sure that in any circumstances mode should not cross right half the plane, otherwise system will become unstable. Although in a open loop case the spiral was marginally stable or unstable, but in a closed loop case you will see it will be stable only. This is spiral mode, you can see finally bring back to this left of the plane. So that is the importance of a closed loop. In closed loop, system should have a stable, right? Like we have seen that in a longitudinal case we have seen the root locus, like we have to see the longitude, fugode mode, short period mode, all mode was lies on the left of plane. So here also we have to check, make sure that our modes is on left of the plane in all the cases. That means delay, theta loop, altitude loop, in all the scenario the thing should be, this loop mode should be not go outside the imaginary line, that means right of the plane. Okay, and we have also seen that there is a many loops involved, right? In a longitudinal case, rate loop, attitude loop, and altitude loop. So each loop have some bandwidth, and already we discussed that most inner loop should have more bandwidth in order to make a immediate correction. Like for example, in a quad rotator case or aircraft case, we have seen that the wind is coming in this direction, so it will try to drag the aircraft or quad rotor in this direction, and you want to move in this direction. So what you will do? Immediate you have to correct. Fast testing you have to take. That means what? Inner loop should have a very fast in order to correct, so that you should not deviate from your desired positions. That is the purpose, that the inner loop bandwidth should be very high and outer loop bandwidth should be low. Bandwidth means if the bandwidth decides how well the input and output are tracked. Okay, so that means, and this bandwidth and robustness are closely related. For example, when you have a slow gain, your system is more robust. When you have a fast gain, your system will be not much robust. Why? Without any formula and theory, you can say when my gain is slow, then I have more time to react. As simple as that, right? So this is all about the lateral autopilot design, but in the next class I will try to analyze the lateral autopilot in more detail, and also we will try to incorporate one more loop, that means heading loop, because as of now we have seen only rate loop, that means this roll rate loop and phi angle loop, and the next loop will come heading loop, because when you take a roll you have to attend some heading. Okay, so that heading, or that you can also call course hold. Okay, so in next class we will discuss this, and we will also try to analyze in more detail. Thank you so much.